here we have our matrix A. 7, 2, 6, 3. We have our matrix B. 1, 3, 1, 5. And we're going to add them together. And the way it works is first row, first column gets added to the first row, first column, and we get 8, and that gets placed in the first row, first column. The first row, second column gets added to the first row, second column. 2 plus 3 is 5. And that's our answer in the first row, second column. Okay. And now we can go look at it. Second row, first column, second row, first column, they get added together, we get 7, and so on. And we eventually end up with our answer, 8, 5, 7, 8 is our matrix. So multiplication, subtraction, they work the same way, element by element. And that's the only way addition and subtraction are defined on matrices. However, with multiplication, there's a couple ways you can define multiplication with matrices and vectors. We'll give some more advanced examples next week, but for now I'll just show you the most simple, which is element by element multiplication. And the key here is you use period or dot times. So we call this dot multiplication. And notice that's distinct from the dot product. We'll just call this dot multiplication, dot multiply. And what this does is says use element by element multiplication. So the same thing with addition, like 7 times 1 gives us 7. 2 times 3 gives us 6. And so on. 6 times 1 gives us 6. 3 times 5 gives us 15. So dot multiplication is element by element multiplication. Right? And so element by element also refers to doing something like squaring. So if we want to square each element, go element by element, square them in the matrix, what we have to do is use dot exponentiation. So dot and then the caret. So here, where we say b dot exponentiation squared, b dot caret 2, what it's going to do is square each element. It'll say 1 squared, 3 squared, 1 squared, 5 squared. And give us, oops, of course you'll notice my mistake there, 1 squared, 3 squared, 1 squared, 5 squared. And that gives us the following matrix, 1, 9, 1, 25. Okay, so element by element math, addition, subtraction, dot multiplication, dot division, dot exponentiation. Those are your element by element operators. Okay, let me just clear some of the rest of the screen to draw attention to those. Plus, minus, dot multiply, dot divide, dot exponentiate. All right, and so just hang on till next week for more examples of multiplication, ways of defining multiplication on matrices. Now I'm going to just show you guys a couple more functions. We have sum and prod for the sum and the product. These are just two functions built into MATLAB. So on a vector, they work really easy. Sum of 3, 5, 7 just adds them together, 3 plus 5 plus 7, and it'll give you 15. The thing is, on matrices it works a little bit different. It sums the columns. So summing this, 2, 3, 4, 2, 3, 6, gives you 5, 6, 9. So summing a matrix gives you the sum of each column as a vector. So if you want to sum every element of the matrix, you could take this, right, this vector of the answers, and sum that. Because summing 5, 6, 9, right, that would give you 11 plus 9 is 20. So in essence, if you take the sum of A, you get the sum of each column. It's a vector. So now if you sum that vector, you get the total sum. Right? And then you can think of all your different laws of arithmetic about why this works. Okay? It's because basically you're summing things, and then you're summing the sums. So it works fine. Right? And product, PROD, for multiplying all the elements, works the same way. Okay? Now let's look at two other functions for finding the maximum and minimum element, largest and smallest element in a vector or matrix. Okay. So if we wanted to find the maximum number of the following vector, 4, 6, 5, just use the max function of 4, 6, 5, and it'll tell us, okay, 6 is the largest number in that vector. Great. The thing is, you can also request two outputs. So notice this is kind of like using size, but here we're requesting two outputs. We want the value and the location. And the val location, those VAL, LOC, those are just variable names. Had I called it, X and Y, this would do the same thing. What we're doing is the first answer is going to be, so here X or value, whatever you want to call your first variable, that's going to tell you the largest element, so 6. The second answer we're requesting is going to tell us the location. So in this vector, notice it's the second element. So the second element is the largest. So here the location, or Y, is going to be 2 for the second element. Okay. And it works similarly with matrices, except it does it for each column. Okay. So here, if we want to know, the maxima, or actually in this example we'll use the minima of this matrix A, the first variable is going to be the values that are smallest in each column. First column, 2 is the smallest. Second column, 4 is the smallest. Third column, 3 is the smallest. Okay, so that's the first variable. The second variable is going to be the locations. So essentially, which row contains the minimum in each column. So in the first column, the first row has the smallest. In the second column, the first row again contains the smallest. However, in the third column, the second row contains the smallest. Okay, great. All right, so now we're going to do something a little bit more interesting. We're going to use MATLAB to go find the row and the column the minimum elements located in. And note, we're in this example looking for a unique minimum, and we're assuming all the elements are unique. Actually, that's actually worth mentioning. When you're finding the maximum or the minimum, it finds the first of the maxima or minima. So here in maximum, let me switch back to pen. If you found the max of 4, 6, 6, 5, value in the location, MATLAB would say, okay, the value is 6, and the location is 2. It finds the first one. Okay, so just keep that in mind. Now we're going to go look and do the more advanced one, finding which row and which column's in. And there's actually a number of ways to do this. There's a very interesting way to do this with modulus, and you convert the matrix into a vector, and then you can play around with the modulus based on the size of the original matrix to get the answer. Think about that method. If you're interested, if you want, I can show you it at office hours, or we can talk about it at office hours. But here, let's look at what, to me, is a slightly more intuitive and easy method. So what we're going to do is do this in 3 steps. So first, we're going to use the minimum function on V. Recall this works on a column-by-column basis. So we're going to basically be creating two variables. Small c is going to be a vector, the smallest number in each column, and LOCC is going to be a vector of, in each column, which row has the smallest. Okay, so in the first column, the smallest number is 2, and that's in the third row. In the second column, the smallest number is 1, and that's in the second row. All right. So now we're going to do something interesting. We're going to say, okay, now let's find the minimum of this vector that we just looked at. Okay. And so we're going to find that what I'm calling the small o, or the smallest overall, the smallest number in this vector is a 1. Which location is it? Well, it's the second location. And so notice something interesting.